Hello, this is Brother Cromar from the Math Department at BYU, Idaho, and this is part 2 of Lesson 13 dealing with the match pair design. And so what I'll be covering in part 2 is confidence intervals and checking requirements. Now let's review some confidence intervals. This is the very first confidence interval you ever saw for this course, where we dealt with one mean where we knew the standard deviation. Here was the formula for it, and we pretty much did that one by hand. But then we posed the question, how realistic is our population standard deviation known? Well, we found out that it's not often that we know our population standard deviation, so what we dealt with was something in Lesson 12, which is the confidence interval where we don't know the population standard deviation. So we use the t-distribution instead. And we also estimate our or our population standard deviation, which is S, which is our sample standard deviation. So this is the formula for one sample t confidence interval. But if you remember, we did the confidence intervals using software, whether it's Excel or SPSS. Now this here, it doesn't say this in the online textbook, but this is the formula for a match pair design, the confidence interval for it. Now as you notice here, here's the formula for it compared to what you see in the last slide here. The structure is very similar. Back in lesson 12, this is X bar here. Lesson 13, D bar, D bar was in the online textbook. D bar represents the mean of the differences. We also add and subtract the critical value from the t-distribution, times it by a standard deviation over the square root of n. Now we did the same thing that we did in lesson 12, but now instead of a pure sample standard deviation, we take the standard deviation of the differences. If you notice here on the right side here is the father-son's data, where we calculate the differences and we get a standard deviation of those differences. D bar also represents the mean of the differences, and so we get the mean of these differences. N is the number of pairs in our sample. So in this example on the bottom right, N is not 26, even though I had 26 observations. N is the number of pairs, which is 13. And then here's the definition for the margin of error, which is everything to the right of the plus or minus sign. But you're not going to do this by hand. You're going to do all this using software, whether it's Excel or SPSS. Here's some example of some output. Okay, so here is, as you see here, this is similar to what you see in Excel. This is SPSS output. You can get the mean of the differences and the standard deviation of the differences. That's the descriptive statistics, which I'll talk about later. You can get the degrees of freedom here in this case, which is n minus 1, which is 12. And then here's where you can get your confidence interval. So how we interpret this confidence interval is that we're 95% confident that the mean of the differences is between negative 2.06 and 1.44. So what I want you to do is stop the video and think for a sec. Based on this confidence interval, can we tell statistically there's a difference between father's heights on average and son's heights? Well, the answer to that is, since 0 is in our confidence interval, there does not appear to be a mean difference in heights between fathers and sons. That's something that's statistically different. Basically, with our confidence interval, we have a possibility of negative numbers or positive numbers. And since it could either be sons being taller or fathers being taller, it's inconclusive. We can't tell if there's a difference. And so a rule of thumb is if 0 is in the confidence interval, we can't tell statistically there's a difference between the two paired groups. Okay. Now let's go through another example. Here's the same example using the weight data, taking a diet and seeing if the diet was effective. So comparing pre-weight and post-weight. So looking at the last sentence, since you are a crackerjack statistician, you would like to construct a 95% confidence interval on the mean difference between the post-weight and the post-study weight and pre-study weight. So what I'm going to do is I'm going to go to some output here. That's not the output. Here is the output here. The output is listed here. This is similar to what you would see in Excel. And so we have two negative numbers. We have negative 8.058 and negative 5.5489. So what we do is how we interpret that confidence interval is that we say is that we are 95% confident that the mean difference in weight is between 8.059 and negative 5.549. Okay, so in this case, can we tell that there is a difference between the pre-study weight and the post-study weight? Well, in this case, since 0 is not in our confidence interval, there does appear to be a mean difference in post-study versus pre-study weight. Okay, so we have two negatives. 0 is not in our confidence interval, and negative means that the weight is decreased, so therefore we can say that there seems to be a significant difference in the reduction in weight on average. Okay, so now the last item I want to cover is checking requirements as well as dealing with descriptive statistics. Now, before doing either, it says here confidence interval, before doing either a confidence interval or hypothesis test, there's 3 requirements to check for matched pairs. Now, there's 2 in the online textbook. I'm going to add one more just to cover my bases here, but there's 3 different requirements. First of all, the sample needs to come from a simple random sample. The sample data, I'll reduce this here, are matched pairs, and that's the one that's not included on the online textbook. And the last one, it's either one of 2 things. The differences are normally distributed, so we do a QQ plot to see if they're normally distributed, or n is large, and by guideline we say n is greater than or equal to 30, where n is the number of pairs. And so if we apply the central limit theorem, if the number of differences is large, we can assume with the central limit theorem that the sampling distribution of differences is normal. So the descriptive statistics that we'll be asking you for is a sample mean and standard deviation of the differences, as well as a histogram of the differences. Okay, so now what I'd like to show you, here's some output in terms of, this is some SPSS output in terms of what you could see, whether it's in Excel or SPSS. Here's the mean and the standard deviation. This is where you can find that here. This is with the pre-weight versus post-weight data. Here is a QQ plot that was created, and it looks like, even though it's a little squirrely, for the most part though it doesn't look too bad. The dots are at or close to the line, so we can assume that the data is normally distributed. Since the number of pairs and the number of differences is 26, it would be wise to look at a QQ plot. Now with the graphs, here's you can use a box plot, but I mentioned in the slides to do a histogram. And here is a histogram of differences. This also lists the mean, which is -6.8, and the standard deviation, which is 3.172. I think also I said that the mean was 6.8. I meant to say the mean was -6.8. And that concludes part 2 of the lesson 13 videos. If you have any questions, please talk to your instructor. Thank you.